Now, I know what you're thinking. That last video showed some marginally interesting variations on the process of creating a Taylor series using the geometric series formula. But every single one of our examples so far was centered around zero. And sometimes we have a function that's not defined at zero. For example, 1 over x. And we can't center an approximation of a function around a point that's not defined for the function. We can't get a tangent line approximation of a vertical asymptote. We can't get a polynomial approximation of a vertical asymptote. That just doesn't make any sense. We've got undefined stuff all up the wazoo at x equals 0. So in those cases, we've got to change the center of convergence, right? We can't center this at 0. We have to center it somewhere else. So in this case of 1 over x, let's center this at x equals 1. And it doesn't have to be 1. It could be literally any number other than 0. So if c equals 1, then x minus 1 has to show up in my formula. Okay? That's just what it means to have a center at 1, is that we've got a whole bunch of x minus 1s in our Taylor polynomial. So we already know, I think, that the sum from n equals 0 to infinity of a times r to the n equals a over 1 minus r, only if the absolute value of r is less than 1. And we want to make sure that we're comparing 1 over x to this. Well, as I just talked about, 1 over x isn't going to cut it, but we want to make sure we have a minus 1 in our denominator. So x minus 1 is what we want to see, but clearly these two aren't equal. If I'm including a negative 1, I'd better include a positive 1 as well. Okay, so I want you guys to look at this equation that I've written, 1 over x equals 1 over 1 plus x minus 1. Convince yourself that they're the same thing. All I've done in the denominator is I've added 1 and I've subtracted 1 to the denominator. So it's still the same thing. I've kept everything balanced. I've just forced that x minus 1 to show up there. All right, so now this looks an awful lot like a over 1 minus r, except for it's a over 1 plus r. So yeah, you're right. We need to change that to, instead of adding a negative, we need to subtract, right, adding a positive rather, we're going to subtract a negative. So we can do negative parentheses x minus 1, but that sounds like too many parentheses. I'll go ahead and distribute the negative 1 into here and get 1 minus x. That's okay, right? Either x minus 1 has to show up or 1 minus x. As long as when we plug in x equals 1, we get a whole bunch of zeros, right? That's what it means to have it centered at x equals 1, is that everything goes away, except for the constant term. All right, cool. So that means that a equals 1 and r equals 1 minus x. Okay, so that means that we can rewrite 1 over x as the sum from n equals 0 to infinity of a times r raised to the n. All right, that's nice. And we know that this is true provided that our r value is less than 1. Now, we can leave it like that. This is a 1 meaning our radius of convergence. But I don't like this as a domain. It's not quite clear what our x values are. So let's expand this out. We know that 1 minus x has to be less than 1, but it also has to be greater than negative 1. Hopefully that makes a little bit of sense. If you've taken Algebra 1, that should make a little bit of sense. Subtract 1 from everything, we get negative 2 is less than negative x is less than 1 minus 1 is 0. And then if we divide everything by negative 1, don't forget, again, going back to Algebra 1, this less than changes to greater than. 0 divided by negative 1 is 0. Negative 2 divided by negative 1 is 2. So our interval of convergence is going from 0 to 2. Always small comma big when you do interval notation. Anyway, that is the domain. You can write it like this, but I think that this might be a better way to write it if they're asking for the interval of convergence. Another note just for those of you who like to write this in different ways, we can factor out that -1 and say this is the same thing as n equals 0 to infinity of -1 raised to the n times x minus 1 raised to the n. It's the same thing, but this way we get that alternating sequence built into it. Oh, and I forgot to write the first 4 terms of this, so let's go ahead and do that up here because I've got space. When n equals 0, I've got 1. When n equals 1, I've got minus x minus 1. I'm using this one. I like this one better. And then when n equals 2, I'm going to get a positive, and it's going to be x minus 1 to the second. And then when n equals 3, I'm going to get a negative x minus 1 to the third, and it's going to alternate plus and minus forever. Okay. We could definitely use this as well. If we change all of these x minus 1s to 1 minus x's, then we would just put plus, 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 plus. So whichever way you like, they're both correct. All right, so let's see if we can combine both of the interesting things, namely centering it somewhere other than 0 and also not having a 1 in our problem. And you might say, well, wait a second, I do have a 1 in my problem. It's right here. It's minus 1. But remember that if we center this at x equals 1, then we need to see x minus 1 in our problem. Okay? So remember, if you forgot, I'll just remind you real quick, that the sum from n equals 0 to infinity of a times r to the n equals the fraction a over 1 minus r, but only when r is between -1 and +1. Okay, so I've got this 15 over 2x minus 1 is my fraction that I'm dealing with now, but I have to have an x minus 1 in here. So the 2 is being multiplied by stuff, so I'm going to replace my x with an x minus 1. But think about what this is. I just actually subtracted 2 from my denominator, so I better add 2 back into my denominator, but I still have this minus 1. Huh, that was a bit messy, wasn't it? But I think if we simplify this a bit, we can see that this is going to be 1 plus 2 times x minus 1. Okay, now convince yourself that if I distribute the 2 and combine like terms, that I'm back to my original denominator. The numerator hasn't changed, and the denominator has been rewritten, but hasn't actually changed in value. So now we can see that a equals 15 and r equals -2 times x minus 1. Now I guess I lied because we still had the 1. I thought the 1 was going to go away. Remember, if this isn't 1, we can just divide everything by whatever this number is. So if this were, say, a 3, for example, I'd get a 2/3 here, and I'd get 15 over 3 or 5 up here. But since this is just a plain old 1, we don't have to worry about that step. So now that we have a and we have r, we can write this as the sum from n equals 0 to infinity of a times r raised to the n. Okay? And if you feel like it, you can rewrite this. I like to maybe sometimes I'll pull out the -1. In fact, you can rewrite this as 3 different factors, all raised to the n. And it's really just a matter of preference. I'm not really so concerned about these as long as you know the difference. In these, I mean, there is no difference, but as long as you understand that there is no difference between these guys, you can write it any sort of combination you would like. And anyway, the expansion of this, the first few terms, the first 4 terms are, let's see, we've got 0, so 15 times 1 times 1 times 1 is 15, and then we're going to multiply the previous term by -2 times x minus 1, and then we're going to multiply the previous term by -2 and by another x minus 1, and we're going to multiply the previous term by -2 and also by another x minus 1. And we're going to keep on doing that positive, negative, positive, negative. It's an alternating series of plus, minus, dot, dot, dot. The only thing I haven't talked about is that interval of convergence. Well, remember that the interval of convergence is for all the values when r is between -1 and +1. So if -1 is less than -2 times x minus 1 is less than 1, well, divide everything by -2. We'll get positive 1/2, negative 1/2. Oh, it's a negative, so we'll flip those less thans to greater thans. And then we've got our x minus 1 is the only thing that's left. Adding 1 to everything, I'll find that we get 3/2 is the big end of things, and positive 1/2 is the small end of things. Our interval of convergence is 1/2 to 3/2.